So we will now study a problem that is really connected to the maximum flow problem. That's the problem of the minimum cut. Okay, in that problem, you have a network that is given here. And the goal is to disconnect, for instance, in this graph, that is the graph of Canada. The goal is to disconnect Montreal and Quebec. So you are allowed to cut some of the edges. And you want to cut the minimum amount of edges so that you disconnect Montreal, any communication between Montreal and Quebec. So one possible solution is this one. Okay, the minimum amount that you should cut is you should cut that one, that one, that one. So that's 4. And we can prove that we cannot cut more than that. Well, sorry, that's the least number of edges that you need to cut to disconnect Montreal and Quebec. And to prove that, you can build a graph like this one, where you put one on every edge, and you find the maximum flow from M to Q. And again, if you look for the maximum flow, you will see that you have the value for the flow is equal to 4. And that's exactly the same as the minimum cut that you needed to perform to disconnect Montreal and Quebec. And that's not really by chance. Actually, the two problems are related, and the minimum cut is always equal to the maximum flow in a problem. This is what we will study. Let's first formally define what we mean by a cut and the net value of a cut. A cut is a bipartition of the set of nodes, and we will call the two partition S and T, okay? The set S and T. The source node S is in the set S, and the sink node will be in the set T, okay? And of course, the two partitions are disjoint, okay? S intersection T is equal to the empty set, and the union of them is equal to V. That's the definition of a partition. And again, S belongs to capital S, and the sink node belongs to capital T. We call the capacity of a cut the capacity of the edges that will link a node from S to a node in T, and not in the opposite direction, right? So only from a node from S to a node in T. So you take the double sum from any node from S to any node in T, you add the capacity of that edge, and you've got, as a result, the capacity of the cut. Let's make sure that we get it right. So if we define the set S and T like this, and you see that 1, that's the sink node, the source node is equal to 1, 6 belongs to T, right? And so what is the capacity of that cut? You take the double sum, and you will take into account that edge and that edge, but not that one, because that one is an edge from a node in T to a node in S, and that's not allowed, okay? So if you remember, the definition is from S to T and not from T to S. And so you've got only 2 edges here, that one, and therefore the capacity of that cut is equal to 8. Okay, a little bit more difficult here. Now we have this node, these nodes in S, so that's S, 1, 4, and 2, 3, 5, 6. What is the capacity of that cut? Okay, let's represent it like that. You will just add every node from a red node to a purple node, and so you will add 2 plus 7. Okay, so you've got 2 plus 7 plus 3. And that's it. So the capacity of that cut is equal to 12. Okay. The net flow of a cut, okay, you can compute it like that. The net flow of a cut, you take a cut, any valid cut, and you compute the sum of the flow from a node A to B, and again, a node, it's only on edges going from a node in S to a node in B. So if this is your current flow in the max flow problem, the net flow of that cut, you will again add 3 and 3. Okay, you've got 3 and 3, but you see that you have 1 unit of flow there. And so by definition, by convention in our flow, that one had an implicit -1 in that direction. And so the net flow of that cut is equal to 5 here. because the flow from 2 to 5 here is equal to -1.